All right. Stop talking, please. Take out your things. We'll start by taking questions. Does anybody have questions from last night's assignment? So again, any homework questions from last time? Kate? 59? Sure. So 59, it asks us to convert the rectangular coordinates given into polar coordinates. And it says to report an angle between 0 and 360 degrees. So the tools that I'm going to use are these two relationships. Okay. So hopefully it's easy to see that my value for r is going to be plus or minus 2 root 2. Now, we have our choice, and I think that by and large there's no reason to ever pick the r to be negative. It just makes things a little bit more complicated. I don't know. Okay. So the next thing we're going to do is we're going to worry about solving for tangent of theta. The issue here, though, is what is the range for tan inverse? It's negative pi over 2 to positive pi over 2, or negative 90 to positive 90. So the angle that is in question lies in there, but the tan inverse is going to report the negative version of it, which is fine. We can deal with that at the end. So in this case, I'll do theta is equal to, actually we'll call this, yeah, theta is fine. Tan inverse of negative 2 over 2. When I type that into my calculator, I get negative 45 degrees. But I want an answer between 0 and 360. So all I'm going to do is find an angle coterminal to this by adding 360. So the theta that I'm going to use is 315. So I have r comma theta. Thank you. Good with that, Kate? Good. Okay. Anyone else with questions from this assignment? Okay. So we'll start today talking about 13.4. This is all about polar functions. Before we start this, though, I want you to recall the definition, the last definition that we gave yesterday, because we're still going to be using this definition today. Can you stop talking, please? So remember from yesterday, these were the definitions that we gave in order to help us convert between a polar coordinate and a rectangular coordinate, or vice versa. Remember that a function is just a set of ordered pairs, right? So if I'm going to convert between a function that's in a polar form and a function that's in a Cartesian form or rectangular form, I'm essentially going to be using the same conversions, right? Since we're just talking about sets of ordered pairs, even though typically we describe a function with an equation, it's just kind of a shorthand for a set of ordered pairs. So just kind of keep these in mind. We'll use these 4 conversions kind of throughout today. I did want to go back and make us rewrite them down, though, since we're going to be referring back to them over and over again here today. So a polar function is going to describe some points r comma theta, right? Now, in this case, we think of the r as our dependent variable and the theta as the independent variable. This is slightly different than the Cartesian form, where the x is typically the independent variable and the y is the dependent variable. So just kind of keep that in mind. Our general form then for a polar function usually starts r equals and then some expression in terms of thetas. Everybody okay with that idea? So most of today, what we're going to do is spend translating back and forth between a function that's written in polar form and a function that's written in Cartesian form or vice versa. So let's start going polar to Cartesian. And let's actually start with this first example. R is equal to 6 cosecant theta. So my goal here in converting this into Cartesian form is to eliminate the r and the theta and replace them with x's and y's. Everybody's okay with that plan? Okay. So it seems then that the 2 equations that would likely be the most useful to me are going to be x is equal to r cosine theta and y is equal to r sine theta. So I'm trying to get those sorts of things so I can substitute them for an x or a y. So I know, or I remember, that cosecant is the same thing as 1 over sine. That was a first semester idea, right? We still have to remember those. And if I multiply both sides by sine theta, notice what we have now. I have r times sine theta. What is r times sine theta equal to? Y. So I can substitute that for y. And now I've eliminated both r and theta in one swoop, leaving me with the Cartesian equation y equals 6. So if I graph the polar equation, r is equal to cosecant theta, what would I expect the graph to look like? Just a straight horizontal line, right? Let's graph that quickly and confirm that that is indeed what we get. So I'm going to take my calculator. I'm going to make sure that I'm in radian mode and polar form. And then I'm going to do 6 times. I don't have a cosecant button, but I can do 1 over sine. And notice here when I press the variable button, the calculator automatically gives me the theta because it knows that I'm in polar form. For my window, the theta goes from 0 to 2 pi is good since the period for cosecant is 2 pi. And then for my regular window, I'm just going to make the usual square window going -10 to +10 for the x's and y's. And then hit graph. And I get exactly what I'd expect, right? So that should confirm to us that we've done this correctly. Okay? Let's do another that's a little less trivial. So, again, I'm just going to write on the right-hand side, x is equal to r cosine theta and y is equal to r sine theta, because these are the equations that I might be needing. If I take a look now at what I have, I notice I have the cosine theta part, but what am I missing to make a substitution? I don't have an r times the cosine theta, right? So what am I going to do to fix that? I'm just going to multiply both sides by r. Okay. So now I have r times cosine theta. Everybody's happy with that? So I can just replace that with x. Which is nice because now I've eliminated the thetas, right? No more thetas in my equation. I still have this r squared though. What should I do with that? Well, remember, there was a third equation that says r squared is equal to x squared plus y squared. James and Juliana, get out of jail free cards for you guys. So, what can I replace the r squared with? X squared plus y squared. Everybody so far so good? I'm now going to move everything onto the same side. So I'm going to subtract 6x from both sides. And what I'm going to do with the x's is I'm going to do a completing the square. Do you guys remember from your Algebra 3-4 course when we did completing the square? You should. We spent a good amount of time doing it. So if I have ax squared plus bx plus c, how do I, actually let's just say x squared plus bx plus c, how do I complete the square? I'm going to add b over 2 squared to both sides. So in our case, we're going to add -6 over 2 squared to both sides. So, yeah. So if I take my x squared minus 6x plus -6 over 2 squared, that's really x squared minus 6x plus 9, right? That factors. What does it factor to? So x minus 3 and x minus 3, or really just x minus 3 squared. So just as an aside, if I have x squared plus bx plus b over 2 squared, that's always going to factor to something that looks like this. Okay? So it's always going to factor to quantity x plus b over 2 squared. Just FYI. So this is my Cartesian form. You should recognize this form of an equation. What shape graph is this describing? Not a parabola. That's a circle. Remember, the graph of a circle is x minus h squared plus y minus k squared is equal to r squared. What does the point h comma k represent? The center. Good. And what does r represent? The radius. So for our equation in red, what would the center of the circle we'd expect here be? Would be 3, 0. And what would the radius be? 3. Let's graph our polar function and see if that's the graph that we get. So 6 times cosine theta. And the window I had from before is fine. I do get something that looks circular. What does it appear the center of that is? You mean 3, 0. And the radius appears to be? So the center looks like it's right there. And if I count 3 units in either direction, up or down, left or right, I run into the circle again. So the radius appears to be 3. Notice that even though this looks like it's an oval, that's just a distorted image because the shape of our screen is rectangular. And the tick marks on the x-axis are wider than the tick marks on our y-axis. So it's really still a circle. Okay. Let's do one more. And then we'll move on to going the other direction, from Cartesian back to polar. So again, I'm just going to start by writing down those now 3 equations that we've found useful. So if I look at my polar equation, what do you think we should do first? Multiply both sides by r is correct. And the reason I want to do that is because now I have an r cosine theta and an r sine theta on the right-hand side. So I can convert those into x's and y's. And I also have, on the left-hand side, an r squared, so I can rewrite that as x squared plus y squared. Everybody okay with what I did there? Okay. So just like I did before, I'm going to move everything onto one side by adding 5x to both sides and then subtracting 4y from both sides. And now I have two situations in which I should do a completing the square. So what do I need to add to the first side to complete the square for the piece in yellow? 5/2 squared. And what do I need to add to both sides to complete the square for the piece in blue? What do I need to add to both sides to complete the square for the piece in blue? -4/2 squared. Okay. Everybody okay there? So x squared plus 5x plus 5/2 squared factors. What does it factor to? It's going to be x plus and then b/2. Okay. What does y squared minus 4y minus 4/2 squared factor to? You mean y minus 4/2, but I'm just going to write 2 there. Everybody's okay there? We're good with y, it's minus, because it's plus a negative. Yeah. And then on the right-hand side, 5 squared over 2 squared is 25/4. And then -4/2 is just -2, and -2 squared is 4. If I make a common denominator and add the right-hand side, I get 41/4. So the circle I'm looking at has center -2.5, comma, +2, and its radius is somewhere between 3 and 4, right? 41/4 is almost 10. The square root of 10 is a little more than 3. Let's check that on our calculator. Oops, that's not the calculator. So I have 5. -5 cosine theta plus 4 sine theta. And we'll just hit a graph. And that center appears to be -2.5, comma 2. And if I count, the radius is a little more than 3. So I'm pretty convinced I've done that correctly, because our picture matches the Cartesian form that we wrote. Everybody's okay there? So now let's go Cartesian or rectangular back to polar. Again, I'm just going to write on the side those 3 equations that we've used here to do these conversions. Again, we might use some of them or none of them, but I'm going to write them down anyways, just so we can refer to them, so you don't forget them. Okay. So, what I want to do is I want to replace or eliminate all of my x's and y's and replace them with r's and thetas. So, what I'm going to do here, I notice that I have y, so I can replace it with r sine theta. Now, typically for a polar function, we want to write the r by itself. So if I divide both sides by sine theta, and remember that 1 over sine is the same thing as cosecant, and that'll do. Let's try something that's a little less trivial. So let's take this Cartesian equation. Again, write down those 3 equations that we might need to use. What do you think we should do as a first step here? I heard somebody mumble something, but I couldn't really hear. Yeah, let's FOIL out x minus 3 squared. So remember that x minus 3 squared is not x squared plus 9. It means x minus 3 times x minus 3. And similarly with y plus 6 squared, that's y plus 6 times y plus 6. Everybody's okay there? Common mistake is students not foiling there and just trying to distribute exponents. Exponents never distribute. It's a good way to embarrass yourself by doing that. Okay. So what I would do next is I would get rid of the constant terms. If I subtract both sides by 9 and then subtract both sides by 36, notice that 45 minus 9 minus 36 is 0. So I have this. Everybody's okay there? Next thing I notice is that I have an x squared plus a y squared, right? So I can make an r squared. And then I have an x, so I can make that r cosine theta. And I have a y, so I can make that part r sine theta. Everybody okay there? All right. I'm going to now get the r squared by itself. So I'm just going to add 6 cosine theta, or 6r cosine theta, and subtract 12r sine theta from both sides. And we're almost home, right? Now the issue is that I need this to start r equals instead of r squared equals. But remind me again, when we're graphing a point, r comma theta, what does r represent? It represents the distance of that point to the origin. Can that be 0? So guess what we can do? Because r is non-zero, I can divide both sides by r. Normally, you don't want to divide by a variable, because if that variable is 0, or could be 0, that's a problem. But since r is a physical distance, it is non-zero, so we can do that, and we're done. Let's just check that this polar graph gives us an equivalent circle whose radius is 3, -6, and whose I'm sorry, center is 3, -6, and radius is somewhere between 6 and 7. So 6 cosine theta minus 12 sine theta, and hit graph. So that radius appears to be at 3, -6. I'm sorry, the center at 3, -6. And the radius is pretty big. If I counted, it's a little bit more than 6, but it's less than 7 still. So I'm pretty convinced that that's correct. We're going to stop here. That's enough for today.